based on our velocity versus time graphs, how do we solve for acceleration? Okay, from a velocity versus time graph, how do you find acceleration?
How much is going up?
Okay. More specifically, how do you solve for it? The slope. Good. Velocity over time, which looks like this equation right here. Okay, since this is on the y-axis, change in y over change in x, that's acceleration. Okay? So acceleration is a change in velocity. It can be both positive and negative. This equation should go on your equation sheet. Okay, the line over the A here is just average. That's all it means is average. I'll never write that line over the A, so you don't have to include that in your equation. Okay, your book does it, so I wanted to show you that way. But we'll always solve for average acceleration, so there's no need to include that line over the top. I will not for the rest of our time. Okay, so this is change in velocity over change in time. What would a negative, does a negative acceleration always mean that we're slowing down? No. No. Okay, just like a positive acceleration doesn't always mean we're speeding up. Okay.
What else can it mean then? We're going backwards?
Kind of. Okay, remember our rule of thumb that we talked about? If an object is slowing down, our acceleration doesn't match our velocity units. Okay, if an object is slowing down, our velocity and acceleration signs don't match. Okay, if our acceleration and our velocity signs do not match, that means our object is slowing down. So let's look at a couple examples of that. So let's just try an example here with some math so we can prove that rule of thumb. Acceleration equals velocity final minus velocity initial over time, right? That's what delta means, right? That's what the triangle means, change in, or final minus initial. So let's look at an example here where an object slows down. Okay, an object slows down. Let's say our initial velocity was 5 meters per second. Our final velocity was 1 meters per second, and it did that in 2 seconds. Okay, so do you agree that we're slowing down here? We're going from 5 meters per second to 1 meters per second? Okay, so we see that we're slowing down. So if I solve that equation to find the acceleration during that point, I take final minus initial over time. Right? That gives me negative 4 over 2. Gives me negative 2 meters per second squared. Okay, our units for acceleration are meters per second squared. Okay, because our velocity on top is meters per second, time on the bottom is seconds. That's where that comes from. So this example is the
5 over 5 minus 1.
Final minus initial. Final minus initial.
You wrote it backwards. Wait.
Final minus initial.
At least you're confident.
Sorry.
That's all right. I make mistakes all the time. I would not be surprised if I did it wrong. Okay, it's okay. Okay, so we're slowing down here. Our velocity is positive. Our acceleration is negative. Our signs don't match when we slow down. So let's look at another example, this time in the negative direction. So our initial velocity, let's make negative 30 meters per second. Our final velocity, let's make negative 10 meters per second. Do we agree that we're slowing down? We're going from 30 meters per second to 10 meters per second.
We're speeding.
The negative only tells us direction. So don't think of the negative as part of the value of the integer, right? That doesn't work.
So we're not going from 30 to 10.
Yeah, we are going from 30 to 10. Initial velocity is 30 meters per second south. Final velocity is 10 meters per second south. Yeah, we're slowing down, right? We're slowing down. We're going in the backward direction, but we're slowing down. Do we agree? Okay. So let's say that took us 4 seconds to do it. Okay, so let's solve for acceleration here. Final velocity minus initial velocity. Negative 10 minus negative 30 over 4. Okay, final velocity minus initial velocity.
How are we gonna know which one's final and which one's initial? Through either.
The word problem will, yeah, the way it's worded, it will tell you. Okay. So when we have two negatives next to each other, what do? We add them together, which gives me 20 over 4, which gives me a positive 5 meters per second squared. Okay, so we had negative velocities but a positive acceleration when we slow down. Okay, when we're speeding up, our acceleration and our velocities should match signs. Okay, the math itself will always prove that. So if you don't want to memorize that rule, don't. Right, just do the math. That's fine. Okay, but that's how it works. That's what I'm telling you. Okay, so acceleration and velocity do not always have to have the same sign. That's what I'm telling you. Okay, they don't always have to have the same sign. I'm talking negative, positive. Okay. Okay, units are meters per second squared, so hopefully we have that down by now. Do we understand why they're meters per second squared? Not really? Okay. Since velocity is measured in meters per second, and we're dividing that by seconds, right? That leaves us with meters over seconds times seconds, which gives us meters per second squared. That's where it comes from. Okay? Let's try one here. These are the types of problems you're going to get in word form. So you have to pick out what those words and values mean, those numbers. What numbers are they giving us? Are they giving us velocity? Are they giving us acceleration? What are they doing? Okay. During a race, a sprinter increases from 5 meters per second to 7 meters per second, 7.5, over 1.25 seconds. What's the average acceleration? So when we start looking at these problems, we will get 4, 5, 6, 7 variables as we move through. So we need to be organized with our problem, which means I like to make a list of my variables over here on this side of my page. Okay. So 5 meters per second, what do we think that's telling us? Initial what? Velocity, good. And that's V sub I. I for initial. What's 7.5 telling us? Final velocity. And then 1.25 is our time. Okay, some people have trouble picking out what these numbers are meaning. If you're having trouble with that, look at the units first, right? Meters per second is always a velocity unit. So that should tell you that this is a velocity and this is a velocity. Then you just need to determine, is it final or initial? Okay, time should be measured in seconds. Acceleration should be measured in meters per second squared. So look at the units to help you determine. So final minus initial. Are we speeding up here or slowing down? Speeding up. So should our velocity and acceleration have the same sign? Yes, they should. Right? They should have the same sign because we're speeding up. Okay, would we agree? Okay, everyone have their calculator out? I know this one didn't really require a calculator, but why don't you grab that if you don't have it out yet? Let's try this one on your own. Moving at a speed of negative 28.6, she slows to a speed negative 24 point, just 24, over 3.2 seconds. Should be part of the is your final velocity minus initial velocity. Tammy, what you have?
I guess.
1.4 what?
1.44 meters per second.
Good, do we agree? Good. Okay. So to go from kilometers per hour to meters per second, do you remember the shortcut? (75) times 0.2778. Tell me what we get there. Should be roughly 24, 25, 23, 28?
20.8.
Oh, 20.8. Okay, thank you. Meters per second. Okay, and is that our initial velocity or our final velocity? Initial. What is our final velocity here?
0.
Good. It comes to a stop. These problems are going to have really kind of in-depth context clues, I guess you could say. Right? It doesn't say we go to 0 meters per second. It says we come to a stop. So you have to know that that means our final velocity is 0. Oops. Okay, since our final velocity is 0, we have to do 0 minus 20.8 divided by 5. And I had it at negative 4.16 meters per second squared. We agree?
Yeah.
Okay. What questions do we have so far about acceleration? If the acceleration of an object is 0, does it mean that the velocity is 0? Oh, just one question actually. I took away the other one. Okay, think about this question with your partner. If the acceleration is 0, does it mean that the velocity is 0? Think about it. Try to give me an example. Okay, so think about. Okay, so these are called your kinematics equations. Then I'm going to give you one, then we'll do a problem, and we'll give you the next one. So here's our first kinematics equation. Okay, these equations are super common, and they can only be used when we have constant acceleration. Okay, which is all of our problems from here on out, pretty much. Okay. So do we know what all of these mean? All of these variables, what do they mean?
Velocity final, velocity initial, something average
Yeah.
time.
Acceleration and time. So acceleration times time here. That's what's happening. Those two are multiplied together. So acceleration times time. Final velocity, initial velocity, acceleration, and time. Okay, and if I take this equation right here and I rearrange it, this is what I get. Right, so it's the same equation, it's just rearranged. Okay, this is the form we'll use more often. Okay, either one will work, but this is the one we use a little bit more often. Okay, it makes no difference though. That's right. That equation should go on your equation sheet. VF equals VI plus AT.
Which we labeled that.
These are your kinematics equations, so you could you can put them all three under here, but that's how you spell kinematics. Put your computer away, please. Okay, let's try this one on the screen here. A bus that's traveling 30 kilometers per hour speeds up at a constant rate of 3.5 meters per second. What velocity is it at 6.8 seconds later? Okay, so as we look at our problem, we're going to start going through and picking out our variables. Okay, what do we think this 30 kilometers per hour is going to be? Good. Initial velocity, and what do we need to do? We got to convert it. That's the shortcut to go from kilometers per hour to meters per second. You could do a T-chart conversion to go kilometers per hour to meters per second. This is much quicker.
30 x, what is it?
Times 0.26. I just am showing the shortcut for going to meters per second from kilometers per hour. Yeah, it started in kilometers per hour, and I need it to be in meters per second. Okay, so this is starting at kilometers per hour. Now this one is in meters per second, which is what we want. Okay? The reason we had to convert, because our acceleration was given in meters per second squared. Okay, so we had to convert that. So acceleration is equal to 3.5. Our time is equal to 6.8. Okay, so that means we're solving for what?
Velocity final?
That's right, velocity final. Okay, I like to just put a question mark so I know what I'm solving for. I know what I have, I know what I don't have. So we can use this first equation. All right, velocity final is what I'm solving for. Velocity initial is 8.3 plus 3.5 times 6.8.
So it would be a different equation for every single one we're solving for. We won't like just use this one and just have t v dx.
You will use this equation every single time. Yeah. In this problem, we just happen to be solving for the one on the, by the equal sign. Nope.
I just said we had 3 different.
We do, but
They're different.
they're just, yeah, they're different equations. They all use essentially the same variables. They're just set up a little different. The next equation will take into account displacement, and the last one doesn't use time. So it just kind of depends on what you have. Okay, do we have an answer? Courtney, what'd you have? 32.1. What's our units that goes with that? Good. Agree?
So are we just forgetting about like squaring everything in that?
What needs to be squared?
When we multiply meters per second squared times
Meters,
per second.
only the unit has anything to do with the square. Okay, so the squared only applies to that second unit. So it doesn't have anything to do with the number itself. Okay, good question. Okay. They get a little more intense as we go. So this is the second of 3. df equals di plus vit plus 1/2 at squared. Nope, I'll always give you an equation sheet. So you have to know how to use them. You don't have to memorize them. So what do we think d sub f and d sub I stand for?
Distance final.
Good. Displacement final. Final and initial. Okay, in these problems, the difference between distance and displacement is usually nothing. Okay, so we're just looking at how far an object has traveled. We have velocity initial again, time, and then 1/2 at squared. So this one, Lauren, you will actually square a number. Doesn't have anything to do with the units, but it has to just do with a square. And this is important, it's just time squared. So it's not this whole term that's being squared, it's just time. Okay, so if you need to put a little parentheses around t squared so you remember, do that. A lot of you will forget to square time. I'm just telling you in advance. You will forget to do it. So just like make the little square extra bold or something. df equals di plus vit plus 1/2 at squared. So what variable is missing from this equation? Be final, right? So this means this would be an equation we could use if our final velocity is not given in our problem, right? So there's going to be 3 different equations, and all of them can be used to solve for something different, right? So here, this allows us to solve for displacement, initial velocity, acceleration, or time if we aren't given our final velocity. Okay? So there's 2 things that will be in all of our equation, initial velocity and acceleration. The rest of them are a little bit more mismatched. Okay, so which one wasn't in the first equation? Displacement, right? So we can't solve for displacement using the first equation, right? We have to use one of the second or the third. All right, here's a little something I want to talk about. D sub I, or our initial displacement, most of the time is set to 0. Because if we say the car traveled 40 meters in 3 seconds, right? We know that our initial displacement, we don't care about where we started, we just know that we traveled a final displacement of 40 meters. Does that make sense? So most of the time, this term right here can be set to 0. So just something to think about. Okay, that won't be given in our problem. It won't say initial displacement is 0. We just have to kind of think about what our problem looks like. Okay, so you have to be able to visualize what's happening in our motion, and we can think about how far it traveled, which would be our final displacement.
So they just have to be 40 apart?
Yeah, like it would, yeah, exactly. We're just looking at that little portion of time where it traveled that 40 meters, so we don't care about really where it started. Yeah. Okay, let's try one with this equation. A train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in this time? Okay, so get written down what you need to. Sydney, can you give me one of our variables here? Doesn't matter which one.
Acceleration 3.05.
Okay, good. Michaela, can you give me another variable?
Time is 1.57 minutes.
Good. And can we keep it in minutes? No. So what do we need to convert to? Seconds. So how do we convert from minutes to seconds? Multiply by 60. Okay, so let's go ahead and do that. Okay. All of our units throughout our problem have to match. Okay, so that's why we need to take time at the beginning to make sure those match. This is meters per second squared. Okay, do we have any other variables that we can pick out?
0 and 40. You can pick another team. 1.
For which one?
Initial would be 0.
Initial what? Initial velocity, yes, would be 0. Okay. And what?
The one would be 40, right? Wouldn't it? V, D. I remember. I'm losing it.
Would displacement I be 0?
That's right. D sub I would be 0. Here's why. We're looking at only this picture of time where our train starts this acceleration of 3.15 meters per second. Right, so our train's moving along, right? I'm going to draw a little train. Okay. It's going to accelerate during this time. So here's that 94.2 seconds, right? And it ends up over here somewhere. Okay, we don't care like where it starts at. This is our starting point. So we're making that 0, and we want to find out how many meters does it travel during this little picture of time that we're looking at. Okay, so we're kind of resetting our origin right here. Right, this is where our starting point is. So our displacement initial is 0. We don't care how far it's traveled up to that point. We just care about this, where we're looking at. Okay, this little picture of time. Does that make sense? Okay. So initial displacement is 0, initial velocity is 0. That makes our equation a lot easier, right? That takes out 2 whole terms of our equation. Okay, we're solving for final displacement. Meters Okay, we only square the time unit. This middle term right here, anything times 0 is what? 0. Okay, so we can just take that out as well. All right, Griffin, tell me what you got.
I got 13.975 kilometers.
Okay, good. 13,975 meters or 13.975 kilometers. We can just keep it in meters, but yeah. You're right. Okay.
Pretty fast train.
Mm-hmm. To go that far in 90 seconds. Right, sometimes when I make up problems, it's like crazy. Okay. I guess. It's a bullet train. Okay, what questions do we have here? Do we understand why initial displacement is 0? And why initial velocity is 0? Okay, when those two are the case, it makes this equation much easier. Right, we drop 2 whole terms out of our equation. So it simplifies it quite a bit. Okay? Are we ready to try another one? All right. You want to try this on your own or one more together? Okay, try it on your own. For displacement, final would be meters. I didn't get a negative answer. Yep. Okay, so our third kinematics equation. Velocity final squared equals velocity initial squared plus 2a final displacement minus initial displacement. So those 3 should go on your equation sheet. Okay, those are your big 3.
The big 3.
The big 3. That's right. We'll use them over and over and over and over again.
Put a box around those and just,
Oh yes, you have a big old box.
Okay, so what equation is missing from this? I'm sorry, what variable is missing from this equation? Time. So this equation allows us to solve for displacement or velocity or acceleration without having time. Okay, so if we're not given time in our equation, this is the one we should use, right? Let's try one and then we'll go downstairs. A car starts at rest and speeds up at 3.5 meters per second squared after a traffic light turns green. How far will it have gone when it's traveling 25 meters per second?
It's a good question. Oh, brother.
Don't get freaked out by word problems. I know a lot of you are.
you gotta break it that much.
The second velocity is 25, right? If our initial velocity, what's our initial velocity?
3 point, no, I'm thinking 0.
Yep, starts at rest, so it's 0. Our acceleration is 3.5. Our final velocity is 25. What are we trying to solve for?
Distance final.
That's right. Distance final is our question mark. So that means distance initial is what?
0.
0, right? That's not given to us in the problem. We just have to know, right? If we're just trying to find out how far it traveled during this time, we don't care where it started, right? We're saying it started at 0, okay? So now we just plug it into our equation. 25 squared equals 0 squared. That's nice. Plus 2a times distance final. And if it's just minus 0, can't we just leave that minus 0 off?
No.
Yeah.
Yes.
You can, or you can leave it. It doesn't make a difference.
I just like to have all numbers in play.
Fair enough.
All players in play. I thought it was 0 minus x. That's not so bad.
Because if it was 0 minus x, yeah, that would make a little bit more difference. But final minus initial, so it's, distance final minus nothing.
Gotcha.
14.3.
I had something.
9.3?
I had 89.3.
Sorry. Oh,
Yeah.
never mind. I think I did it a little bit different.
Okay, since this is 0, we can drop that. 2 times 3.5 is 7 times distance final, right? We're multiplying all those terms together. Since this is 0, we don't need that there. So then we're just going to divide over distance final. That leaves me with 89.3 meters. Okay? A car accelerates at a constant rate from 15 meters per second to 25 meters per second while it travels a distance of 125 meters. How long does it take to achieve this speed? So, let's start picking out what variables we hear. Is anything jumping out at you? We have 2 velocities. So what's our initial velocity?
15.
And our final velocity is? Okay. Do we have an acceleration? Okay. And what are we trying to solve for? Trying to solve for time. Okay, do we have our initial displacement or our final displacement? Final. So what's our initial displacement? 0. Okay, so we need to solve for both acceleration and time. Can we do those both in this equation? No, what can we do in this equation? We can solve for acceleration. So this is another 2-part question. Okay, you have to solve for acceleration first, using this equation, and then we can go solve for time using our easy equation. Okay? Sydney, are you going to make it? Okay, does anyone have an acceleration they want to share yet?
1.6 meters per second. Oh, that's right.
Not the right units. Should be meters per second squared. Okay, acceleration is meters per second squared, but I did have it at 1.6. Okay, so we're squaring the 25, then we subtract over 15 squared, then we would take it 2 times 125, which is 250.
Why would you subtract?
Since our variable's right here and it's got a plus sign between them, right? So if I want to get, this is 625 equals 225 plus 250 times A, right? Do you agree with that so far? Right? I'm just distributing this 2 throughout. Right? Maybe not even distributing, just multiplying those across. So now I need to subtract this to get A by itself. So divide by 250, divide by 250. So A I got to be 1.6. And then how do we solve for time? What equation?
40.
400, sorry. My bad. My stylus is on the outs. Okay, so now what equation can we use to solve for time, since that's our overall goal? First, second, or third? First. We could use the first or the second. Which is the simplest? The first, right? The first is the simplest. So that's VF equals VI plus AT. Is that what we had? 6.25 seconds? Okay, so you need to understand that not all of your problems will be one equation type problems, right? This one required 2 steps. The one before required 2 steps. So you might have to go through 2 equations to get there. Okay? This last one here I'm going to have you try on your own.
Yeah, what's the final answer?
6.25. Okay, try this one on your own. I'm not telling you what equation to use this time. Okay, so you got to pick it out. Race. So for this problem, you should have used your first or your easy equation to solve for acceleration, right? That would have been the simplest way to solve for acceleration. You could have technically, no, you would have had to use the first one, okay? And then to solve for distance final, could you have used the second or the third? Yeah, you could have used either one. Was anyone that used the third equation instead of the second? Right, I used the second. Did anyone use the third equation? The VF squared equals VI squared? Okay. If you did, you should have gotten the same answer. Right? It would have worked out the exact same. Okay? All right.